learned about the idea of a probability distribution, and we talked about them. We talked about probability distributions. We talked about what they are, your x-coordinate, your possible values for the x-coordinate are the domain of your random variable x, and the associated dependent variable, or y, is probability of xi, where that probability is really the frequency of that particular value divided by the total number of values. And specifically, we were talking about discrete probability distributions. Then we had a sketch of one, and then we did one in a table form, and we specifically talked about binomial probability distribution. Now, what are the criteria of a binomial probability distribution? Does anybody remember? What are the criteria of a binomial probability distribution?
Success and failure.
Those are the two options, P and Q. They sum to 100. What else? What else about P and Q from trial to trial?
They must be independent and
P and Q must be independent? How can P and Q be independent? If P plus Q is equal to 100% or 1, they're clearly dependent on each other. That's not. P and Q are constant from trial to trial, right? Because the trials are independent of each other. So the probability for success from trial to trial does not change. Probability of failure from trial to trial does not change. And we generated this formula, right? Right? And we used it for rolling dice or something, right? We created an example, remember? And we generated a probability distribution. And this portion, why was this coefficient there again?
Oh, because of order.
The tricky part. Yeah, because in the simplest, I mean, the book would simply say that, well, if you're talking about 2 successes out of 4 successes, when you just write this, you're generating your successes on the first 2 trials. But who's to say that your successes couldn't come on trials 1 and 3, or 1 and 4, or 3 and 4, and so on and so forth. So it gives you all the combinations, all the different ways success can occur amongst the total number of trials. Okay. And we did it for a set of dice, or for a die, I can't remember. What did we do it for, a pair of dice? No, multiple rolls of 1 die. Well, you can have any number of problems, okay, involving success and failure. You can have multiple dice and so on and so forth, as long as you define the question with success and failure, and with the notion that the likelihood of success and failure are constant from trial to trial, then you have what is called a binomial probability distribution. Okay, that's one type of distribution. Another one that they expect you to be familiar with in high school is geometric probability distribution. And it shares commonality, or rather it has commonality with a binomial distribution. So I guess we can write here, the first one we did was binomial. Now, by the way, all these distributions that we are doing at this stage of the course are discrete, they're not continuous. So we had n choose x, p to the x, q to the n minus x, or n choose x, p to the x, 1 minus p to the n minus x, where p, q are constant, and the only outcomes per trial are success and failure. So now we can do probability of geometric, and it's going to be very similar. We're not going to have the n choose x anymore. We're going to have p to the, remember, in a geometric probability distribution, you keep on failing until you succeed. So we would have q to the x times p, I believe. Okay, so what is a geometric distribution about? The commonality between a geometric distribution and a binomial distribution is also in a geometric distribution. Q and p are constant from trial to trial. But the scenarios that a geometric distribution are used for are different. And they go as follows. Let's say you wanted to calculate, let's say you had a game where, let's say you were playing a multi-stage game, I don't know, with cards and dice or whoever. And let's say the objective of the game was to get to the end. The first person who gets to the end wins, right? Let's say there are 10 stages in the game. Let's say the first stage involves rolling a die and getting a 5, okay? So the idea is that the moment you get a 5, you can then move on to the next stage. You guys with me so far?
Yeah.
Somebody might be lucky, might get a 5 right away, and they move on. Somebody might not be as lucky, they roll once, they got a 3, they roll again, maybe they got a 5 on the second try. And theoretically speaking, there could be some poor schmuck who rolled till he died at age 82, and mid-roll at age 82 he saw a 5, but he was too old and he had a heart attack before he even saw it. And theoretically there's someone somewhere, someone in the world that might roll all their lives and never ever get a 5.
Really?
Well,
There's
it's possible, there's a chance. Now, what might that distribution look like? Well, I think one thing we should do is, oh, we don't have to do that first. So in that particular case, if you look at a probability distribution like that, here's your random variable x. X is going to be defined as rolling a 5 from a single roll of one die. What's the probability that you succeed on your first trial, Gary? 1 out of 6, so. I'm going to make that higher, actually. Okay.
Why do you make that high?
Some of you already know I'm making that higher. And, no, this is wrong. Sorry. Number of failures before achieving a single success. And we'll define P as the rolling a, what did we say, a 5?
Yeah.
From a single die roll. So, if x equals 0, that means that you never failed, right?
Yes.
You took your first chance and you won. Now what's the probability of winning without failing? 1 over 6, right?
Yeah.
Now what would be the probability that you failed the first try but won the second try? That is to say, x would equal 1, meaning you failed once before you had the one success.
1 over 12. 1 over 36.
5 over 36.
Yeah.
I think it would be 5 over 36, right? Because you have to fail first, right? You have a 5 out of 6 chance of doing that. And then again, you have a 1 in 6 chance of succeeding. So that's going to be 5 out of 36. Now, is that going to be bigger or less than that?
Nice. Way less.
Because notice, in the first case you have a 1 out of 6, and in the second calculation you still have that 1 out of 6, but before it you have a 5 out of 6. Now 1 times 1 out of 6 gives you back 1 out of 6, but 5 out of 6 is less than 1, so 5 out of 6 times 1 out of 6 means you're only taking a fraction of 1 over 6. So, what do you guys say this? Well, let's write it as 1 over 6 times 5 over 6, just so we have it, or actually, let me write it as 5 over 6 times 1 over 6. Now, right, so the first data point is 1 over 6, the one underneath is 5 over 6 times 1 over 6. Now, what about failing twice? How many 5 over 6s are you going to have? You're going to have 2. So you're going to have 5 over 6 squared times 1 over 6.
5.
And so what you see is that you end up with a horizontal asymptote of 0, right? Now, do we draw a curve of best fit here, yes or no?
Yeah.
No.
No.
This is discrete probability. In a scenario like this, you cannot fail half of the time. You cannot say, oh, well, what's the likelihood that I half fail or I a quarter fail? You cannot do this, okay? So what's interesting to note here, of course, is that when are you most, if you were to repeat this game multiple times, when are you most likely to succeed? Your first time. That's your biggest likelihood of success, okay? Your first time. And the reason why is because you'll notice the 1 out of 6 for each of these successive ones always exists, but you're multiplying by a value less than 1 each time. And a sequentially smaller and smaller value of 1, or a smaller percentage.
The 5/6, can it be treated as the waiting time of having a success?
The 5/6 is going to be the probability of failure per trial. Here, this is trial 1. This is trial 1, trial 2. 1/6 is the success rate. Q is the failure rate. Now they talk about waiting time. So what do they say about waiting time? Let's take a look, because I can't even remember.
Let me find it. Waiting time.
We talk about expected value. We're going to go back and do the expected values later. We're not going to do them now. And now we have looked at binomial, and now we have looked at geometric, right? And we also looked at the general definition for a discrete probability distribution. We did that. So next to this now I can write 2 probability geometric of X is going to be multiple failures, P and or whatever, where just like with this one, P and Q are constant and the only outcomes per trial. So in a sense, this is what I would call pseudo binomial. So there's a binomial aspect to this because you only win or lose. There's a duality there. There's no bronze medal or silver. There's no silver medal. But, so pseudo, it's sort of like binomial. But X is defined as number of failures before single success, at which time the model stops. And hence you don't have anything like that over there. So we've got 2 down, right? For the ones that you're expected to know the specific equations of. So now we can look at hypergeometric probability distribution. The hypergeometric. Again, this one is also going to be discrete. And hypergeometric probability distribution will apply to scenarios where trials are dependent on one another. So in this particular case, we can say trials are independent from one another. And this is also saying the same thing. No. Did I write P and Q are constant? Oh yeah, right here. This actually should only be here. The fact that it's only P and Q has nothing to do with it. So the P and the Q being constant really is what is the mathematical marker of the fact that trials are independent. Much like pulling cards with replacement. Probability of drawing an ace, as we said yesterday from standard deck of cards, is 4 out of 52. If it's with replacement, the probability of drawing an ace on your second trial is still 4 out of 52, because once you drew the ace, you put it back in. However, if it was without replacement, 4 out of 52 then becomes either a 3 out of 51 if you succeeded before, or a 4 out of 51 if you pulled something other than an ace the first time, right? So in the case of pulling cards without replacement, the probabilities of your second stage differ depending on how your first stage turned out. If you're putting cards back in, probabilities are flat, because each trial deals with the exact same. This and this, right?
Yep.
Do I have to go back over this? Yanjun, did you catch this?
Yeah.
This little thing? I talked about that? Okay, so then you only missed when we started here. Okay, so the next one that you guys are responsible for is hypergeometric probability distribution, and it corresponds to a scenario where the probability of success and failure from trial to trial now change. So you have dependent probabilities, okay? Much like when we talked about the idea of drawing cards from a deck without replacement, okay? Depending on whether or not you had success on a previous trial will yield different probabilities for success or failure on the following trials, okay? We talked about an example here where I asked you to create a probability distribution for the number of nurses possible on a 4-person hospital committee to be formed from 5 nurses and 6 doctors. Didn't say anything about that committee, for this example anyways, I didn't say anything about that committee having particular roles, that is to say the first nurse is going to be a doctor, the second nurse will be the lawyer of the committee, the third nurse will be the administrator of the committee, none of that. And so we came up with this solution where X represented the number of nurses on the committee, anywhere from 0 to a maximum of 4, because the committee size is 4, you can't have more than 4 nurses on the committee. First case corresponds to 5 nurses taking none, 6 doctors taking 4. So this option means 0 nurses, which corresponds to all doctors, divided by 11, choose 4, because you have 11 total people, you want to take 4, and the denominator corresponds to the universal space, right, of choice. And we also point out that these are X by Y calcs for our numerator, that is to say you're grabbing data from different or separate pools, therefore order is not being injected in this case, nor should it be, based on the problem's constraints or criteria. How we develop this pattern, right? So from there, hypergeometric, we can develop an equation, and there are different ways that we can do it. I guess ultimately to be consistent with the textbook, we should probably use the same notation they use. I'm fairly certain, if I recall, they use n for total number of I guess, values of x, maximum value of x, right? I think R, they probably use R for the number of, I'm not sure. How do they do it? How do they choose their variables? Because we can see our pattern here. R is probably, I'm going to guess R is the number of, the total sample space for success. Is that right? Or am I wrong?
The probability.
So do they start out with like an R choose X?
No, ACX.
Okay, so they use A. They use A. Okay, so if they use A, and then I'm assuming they're going to use n minus A,
Yeah.
and then they'll probably make this
R minus X. No, no.
Yeah.
Yeah, R minus X. R minus X.
R minus X.
Yeah.
Okay, X is the total number of successes. This so R is going to be this committee size, right?
The probability of X successes in
And
R
then this is
dependent
going
choice.
to be n. Choose R, I imagine. Is that how they have it?
R is the.
Is that first? Let's see if that's the way they have it. Is that the way they're writing in the book? Okay. So A corresponds to total number of available successful choices. Agreed? We already know what X is. What is N? Total number of choices, period. What is R?
People, maximum amount of like entities in this combination.
Total number of objects that must be chosen, which we are making a constant. For each case, or from case to case. And I think that's it. Have we defined every variable? I think we have. Right? There's an A, there's an X, there's an N, there's an R. One definition, two definitions. Okay? Now, there are no P's and Q's here. You have no constant probability of success. Right? You have no constant probability of failure. Doesn't exist. Okay, in this particular case. Okay, so that's hypergeometric. Now, the other thing that the book does, which I kind of don't like, I've told you, generally speaking, I don't like whenever something is introduced that we don't show you from scratch. But having said that, you need to utilize these formulas, and you'll have them available to you. Yes?
Can we use calculator to do this?
I don't know. Probably it won't matter. It won't help you really that much either way on the test. And that's the idea of expected value. So yesterday I taught you that expected value is average. Okay. Remember, and we talked about the difference between defining average in the way I've shown you before versus the expected value way, right? So I believe that for each and every one of the three distributions that we've discussed, the binomial, the geometric, and now the hypergeometric, we are expected to know the expected value for each of these distributions, which is the average, or the most likely outcome for each of these distributions, okay? So if we go to binomial, we look at the book, which is 7.2, I believe. Let's see what it says about expected value for a binomial distribution. Okay.
Do we have to remember all these equations?
It depends. I'll see what Gallo says.
Depends.
Okay. It depends on what I'm not big on forcing people to memorize formulas, but we have to agree. Okay, so if we take a look here,
Which page?
page 380.
Yep.
They say that the expected value for a binomial.
Yeah, Yeah, it's physics.
probability
It's physics.
distribution
I'm still thinking out of there.
is going to be equal to
Share with me.
NP.
What was the expectation, sir?
Expectation or expected value is the average value for a particular distribution.
Oh.
Now, I'm sure Gallo won't be doing this for this class, but we can do this for fun. They say that this,
For fun?
sorry, and this is not,
Math
did
is
they
not
write
fun.
it? This shouldn't be,
It's a capitalized.
it should be, and I don't even think it should be, I'm just wondering if it should be X.
So the book has.
You roll a capital X.
Capitalized.
Yeah.
Yeah, I know, that doesn't matter.
No, I think it matters.
No, it doesn't matter. To me, it doesn't matter. It's a notation thing. The book will use a lowercase x to represent one particular value.
Yeah.
X, capital X is the entire domain, like the general. It doesn't, to me, it doesn't matter. Okay, so let's pause this for a sec, okay? Because I want to think. Actually, if I'm going to do it the right way,
No, it's
there should be a weight associated with each, right? So,
That's the wrong way.
well, it's right, but it's not using. Remember, our definition was going to be P X I times XI, right? Okay. And it, yeah, and
No.
how did I write the formula for you? Yeah.
PXI is
You have to use sigma.
Yes, we want to add them all up. That's right. So, in your first trial, what is your probability of success? Or actually,
Well,
it's going to be one. It's going to be 1 over n, isn't it?
yeah.
And then you're going to have
And minus 1.
x1. But what is x1 in this case? It's going to be p, I think. It's not going to work. I have to think about this.
So you're saying this is not going to be on the test?
I didn't say anything yet.
You said we're going to do this for fun?
Yeah, we're doing this for fun, but I'm not doing a good job of it yet. Okay, let's pause. Let's think. I think that makes sense, yeah?
I have a question.
Yeah.
What does this E binomial represent? Like,
We want to know on average how many successes you would have for a binomial distribution with n trials. Now your logic is good, and I agree it's great. For binomial, you don't necessarily have to do this. But I want you to become familiar with this because this is the kind of methodology you would have to do if you were going to do geometric or if you were going to do hypergeometric. Right? I mean, this is how I defined average for you using the expected value notation, right? Now what I want you to do is look through it and see if it makes sense so far. See if that makes any sense. If it makes sense, then somehow, you already know, somehow we know that this whole thing has to work out to equaling NP. And the question is, does it? That's really the question. Does it work out to being NP?
Maybe.
Maybe? Does that pattern over there look familiar at all? It's not quite Pascal's, right? Because, well, you see the Pascalness in it, sort of, right? You see